11.2 series. The current record for computing a decimal approximation for pi was obtained by Shigeru Kondo and Alexander Yi in 2011. It contains more than 10 trillion decimal places. What do we mean when we express a number as an infinite decimal? For instance, what does it mean to write pi, 3.14159, and so forth? The convention behind our decimal notation is that any number can be written as an infinite sum. Here, it means that pi equals 3 plus 1 over 10 plus 4 over 10 squared plus 1 over 10 cubed plus 5 over 10 to the 4th power plus 9 over 10 to the 5th power and so forth, where those 3 dots indicate that the sum continues forever. And the more terms we add, the closer we get to the actual value of pi. In general, if we try to add the terms of an infinite sequence, open bracket a sub n close bracket, from n equals 1 to infinity, we get an expression of the form a plus 1, a sub 1, a sub 1 plus a sub 2 plus a sub 3 plus ellipsis through a sub n plus ellipsis, which is called an infinite series or just a series, and is denoted for short by the symbol, the sum from n equals 1 to infinity of a sub n, or the sum of a sub n. Does it make sense to talk about the sum of infinitely many terms? It would be impossible to find a finite sum for the series 1 plus 2 plus 3 plus 4 plus 5 through plus n. Because if we start adding the terms, we get the cumulative sums 1, 3, 6, 10, 15, 11. And after the nth term, we get n open, n plus 1 close over 2, which becomes very large as n increases. However, if we start to add the terms of the series 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 all the way through 1 over 2 to the power n, we get 1/2, 3/4, 7/8, 15/16, 31/32, 63/64, all the way to 1 minus 1 over 2 to the power n. The table shows that as we add more and more terms, these partial sums becomes closer and closer to 1. See also figure 11 in a preview of calculus, page 6. In fact, by adding sufficiently many terms of the series, we can make the partial sums as close as we like to 1. So it seems reasonable to say that the sum of this infinite series is 1, and to write the sum from n equals 1 to infinity of 1 over 2 to the power n equals 1/2 plus 1/4 plus 1/8 plus 1/16, all the way through 1 over 2 to the power n, continuing, equals 1. We use a similar idea to determine whether or not a general series, open, 1, close, has a sum. We consider the partial sums. S sub 1 equals a sub 1, s sub 2 equals a sub 1 plus a sub 2, s sub 3 equals a sub 1 plus a sub 2 plus a sub 3, s sub 4 equals a sub 1 plus a sub 2 plus a sub 2, s sub 4 equals a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. And in general, s equals a sub 1 plus a sub 2 plus a sub 3 plus all the way through a sub n equals the sum from I equals 1 to n of a sub I. These partial sums form a new sequence, open bracket s sub n close bracket, which may or may not have a limit. If the limit as n approaches infinity of s sub n equals s exists as a finite number, then, as in the preceding example, we call it the sum of the infinite series, the sum from a sub n. Definition 2. Given a series, the sum from n equals 1 to infinity of a sub n equals a sub 1 plus a sub 2 plus a sub 3 all the way going on into the future. Let s sub n denote its nth partial sum. S sub n equals the sum of I equals 1 to n of a sub I equals a sub 1 plus a sub 2 plus all the way through a sub n. If the sequence open bracket s sub n close bracket is convergent, and the limit as n approaches infinity of s sub n equals s exists as a real number, then the series, the sum of a sub n is called convergent, and we write a sub 1 plus a sub 2 all the way through plus a sub n plus continuing equals s, or the sum from n equals 1 to infinity of a sub n equals s. The number s is called the sum of the series. If the sequence open bracket s sub n close bracket is divergent, then the series is called divergent. The sum of a series is the limit of the sequence of partial sums. So when we write the sum from n equals 1 to infinity of a sub n equals s, we mean that by adding sufficiently many terms of the series, we can get as close as we like to the number s. Notice that the sum from n equals 1 to infinity of n of a sub n equals the limit as n approaches infinity of the sum from I equals 1 to n of a sub I. Restating that the sum from n equals 1 to infinity of a sub n equals the limit as n approaches infinity of the sum of I equals 1 to n of a sub I. Sidebar, compare with the improper integral. The integral of 1 to infinity of f of x dx equals the limit as t approaches infinity of the integral of 1 to t of f of x dx. To find this integral, we integrate from 1 to t and then let t approach infinity For a series, we sum from 1 to n and then let n approach infinity.